Good afternoon all. So thank you for the organizers for letting me speak on this occasion. So I'll be today talking about hairy black holes in a box. So first let's consider the motivation. So the general understanding is that the black holes in asymptotically flat spaces are completely specified by mass, charge and angular momentum. This lack of hair is one which has some consequences while defining the information paradox, at least at the classical level. So there are many examples of evading no-hair theorems. Some of these are like attracted black holes, and we can change the asymptotics and etc. So another place where the hairy black holes were constructed was in ADS space, which was by Hartnoll-Herzog-Horowitz in 2008, which was the basis in which they set up the holographic superconductor. So, what is so different about flat space? What's so similar about flat space box and ADS? The basic difference between asymptotically flat space and ADS is that unlike asymptotically flat space, ADS has a time-like boundary. So this could be the same if we consider our flat space to be truncated at some RB which is finite. So the natural question would be, can we evade flat space no-hair theorems by putting the black hole in a box? So now let's first just look at global ADS 4, which was done by us in earlier this year. So this was done entirely to build intuition towards working towards the box. So the Poincaré patch actually was analyzed by Hartnoll-Herzog-Horowitz, and the full phase diagram of it was classified in this paper by Horowitz. So apart from global ADS itself, there are three asymptotically global ADS solutions that are there. One is the RN-ADS black hole, which has no scalar. Then there's a configuration called the Boson Star, which has no horizon, but it has a non-trivial scalar condensate there. And then there is the hairy black hole, which is a Reisner-Nordstrom black hole, which has a scalar. So global ADS if you keep increasing the chemical potential of global ADS, it will eventually transit by a second order transition to the phase of a boson star. And this chemical potential is effectively decided by the scalar to Maxwell field coupling. And similarly, the RN-ADS develops the scalar hair above some particular value mu BA, which is a function of both the charge, the coupling constant, and RH. So boson star and hairy black hole, as I said, are second order phase transitions from global ADS and RN-ADS respectively. And the phase diagram is evaluated in the grand canonical ensemble. What we find is that for Q greater than 1 and Q less than equal to 1, there are two different types of phase. So this is for Q greater than 1. So you can see that all four phases exist here. The global ADS to boson star transition, here the temperature is arbitrary, and the transition happens around 0.2 for Q equals 10, which can be analytically determined. And the remaining is a fully backreacted solution. This small blue curve is a global ADS to RN-ADS transition, which is given by the Hawking phase transition. And the next one is the green. So this is a first order transition that's fully analytically computed. Now to evaluate this green line, basically it's the first order transition between boson star and RN-ADS, where one side is a fully backreacted solution and the other side is completely analytically fractal. So it's a semi-analytic sort of approach that goes in there. And this is the line that defines the boson star, the black hole instability, above which the hairy black hole phase becomes dominant. And so this is a second order transition again. And between the hairy black hole and boson star also, there is a first order phase transition. And this structure remains the same for a Q greater than 1. For Q less than 1, what happens is that the global ADS, effectively, if you remember the Hawking page transition, without just the pure Einstein-Maxwell system, then this is T and mu. So what happens is that the boson star instability will happen above this point. But since the global ADS phase is not present there already, this phase, the second order transition, doesn't occur. So that phase is entirely removed. So for Q less than equal to 1, the entire phase diagram is dominated, is completely fulfilled by 3 phases without the Boson Star effect. So this is the full Hawking page curve, and then there is a place where the RNADS black hole becomes the hairy black. So now, before we start, we'll define some quantities in flat space. So this will be the action that we'll be working with. And we'll be looking at spherically symmetric and time-independent solutions with this particular answer. So one thing is that the scalar considered here is a complex scalar, but since we are looking at spherically symmetric solutions, this complex scalar can be written as some constant phase times a real scalar, which the constant which can be reabsorbed by a gauge transformation of A. So which is why we can look at just a real scalar, and this will be the metric answer. And the equations of motion, there are 2 scaling symmetries, just a technicality. So one of which we use to set RB at 1. So the RH has to be always less than RB. And the other one is that is a time rescaling freedom, which we at the end use to set the time component of the metric at R equals RB to be 1. This means that the flat space and any non-trivial geometry will have the same boundary metric at R equals R. So some more definitions again, like, so the quasi-local energy can be defined using the Brown-York definition at R equals RB, this way, where K is the extrinsic curvature of the 2 sphere embedded in the required geometry, and K0 is that of flat space. So it's just a background subtraction scheme. So the temperature for the metric that was given earlier with the rescaling done so that the time circles are the same at R equals RB, it will yield a temperature that is given in general, like in such a form. And the chemical potential is just defined to be the value of the gauge field at the boundary, and the charge is defined using the following. So let's first look at some scalar-less equation, scalar-less solutions. So the first one to look at would be the Schwarzschild black hole, which has G of R usually, and H of R is defined to be just 1 over G of RB, which means GRB, HRB at R is 1, and phi is 0 and psi is 0. So this is the temperature, and the Brown-York quasi-local energy can be complete. Another thing is that from here one can see that for any given value of temperature, you have 2 solutions for RH, which is like a small and a big black hole. So also one could see that there is a T minimum which could be defined for this case. The plot will illustrate this much more clearly. This is a T versus RH plot. So RH is less than RB. So you can see that the T has a minimum, and there are 2 solutions for any given temperature. So also the free energy of the Schwarzschild solution is can be computed to be this. And if you plot F versus T, this gives such a curve where F goes negative beyond RH is 8/9 of RB. And this plot is very reminiscent of what one would find in global ADS, the usual Hawking phase transition. So that's one another motivation that gets you started towards looking at hairy black holes, whether it can exist inside them. So now let's look at RN black hole. The RN black hole's phase structure is a bit more involved. So this is just the general solution. So I have redefined Rn to be some epsilon times RH, wrote the calculations from here. And one could go about computing the temperature, chemical potential, and the free energy. And setting F equal to 0 yields epsilon equals to 2 of these solutions. One of the epsilon equals 1 is the usual extremal black hole. And this one, which is of more interest, gives the Hawking page-like curve for the box case. So if you look at the phase diagram, it looks, unlike the global ADS case, which here, for example, it went up to 0, where at t equals 0, the black hole size was also going to 0. Here you start from the Schwarzschild, which has RH equals 8/9, and as you keep going up higher and higher in mu, the black hole also asymptotically becomes bigger and, not asymptotic. It becomes bigger and approaches the size of the box itself. And around this point, it becomes almost box size. And this red curve is basically a cutoff coming from the finiteness of the box. So along this, the black hole is actually the box size. So to illustrate that a little more clearly, I'll just look at another plot. So this is a parametric plot of, so the red line is basically this cutoff, which is essentially, so this plot is a parametric plot of all black holes with RH greater than 8/9 and epsilon going from 0 to 1. So this is the chemical potential and this is the temperature. So, mu and Ts. So what happens is that, if you are taking RH going to 1 and epsilon going to 1, basically mu and T will go to some finite value. This is what's effectively happening here. So is as big as the box, and there you will get some finite value of mu and T instead of, so which is why this, so this curve looks like arbitrarily cut off at some finite T, but it effectively is becoming the box size where it's like a natural end to the diagram. So the Rn black hole exists, the big black holes can exist only in this region, which are free energy less than 0, thereby thermodynamically. It's the saturation kind, like the box is being filled with the black hole itself. So the extremal one is just T equals 0, mu equals 1 point. So that I have not included in this because that's just a point. Yeah. So also it's not that it's T is not some finite value. Coming from where? Oh, so this is a background subtracted. So you set the free energy for the flat empty box to be 0. Yeah, yeah. So the constant piece is subtracted away. And then, so essentially, that's how you can compare it directly with between flat space boxes. This is positive. So this is like thermodynamically stable as well. So if you look at that, for each of the Q values, you can basically get curves like this. So if for larger Q, what you will get is something like this. So we are looking at large black holes, which means you'll have stable solutions. So actually this free energy was computed effectively in this paper by Brad and Brown, York, and etc. in 90s. But they computed essentially only the specific heat and the local thermodynamic stability of these black holes, but they didn't go any further with the analysis of the full phase structure. Any more? So, so now we'll try to see how to include the scalar into the system. So, yes, yeah, it's usually what you can do is the counter term subtraction. Yes. For here, Like there is no prescription of defining counter terms in this case. Yes. So what one can, this effect, free energy, you can compute in two ways. Like you can directly evaluate the action, or you can use the Brown-York definitions that I have given here and compute. And these give the same result for the free energy. Yes. So you can check all the thermodynamic identities. Basically, del E by del T gives you S. Sorry, del E by del S gives you T, and del by del Q gives you V. All those identities are satisfied. Actually, in this Braden et al. Paper, what they had done was they just computed the E minus. They just put it as E minus Ts minus mu Q. E, they took it to be the Brown-York definition, and then they looked at the saddle, what values of beta and mu will give them the saddle, and they also ended up finding the same values of basically mu and t. Here, the approach is different because what we have done is like by hand set the boundary conditions of the metric to be the same, and then calculated each quantity appropriately, and then directly once you compute it, just with background subtraction, all you get is the same. Actually, the background subtraction is not a necessary thing here. That also one should be precise, because there is no divergences if you are looking at a finite box. Yeah. Yes, but so for the scalar-less solutions, actually, this you can directly take the RB going to infinity limit, where you will reduce to your usual asymptotically flat space computations that already exist. Any more? Okay, so now let's see what the scale, how the box is making things different within in even the flat space case. So if we are looking at the no-hair theorem, what one could do is that you could take the equations of motion that you get from the action, and take from RB, which is at infinity, you can do a series expansion of all the functions G. So we haven't looked at any so the way of defining the no-hair theorem actually manifests in a different way in the case of a box. Like how you can see that it can be. No. Yeah, it's just the usual R3 with some finite cutoff. Yes, S2 process segment. It's a spherical cavity, to be very precise. But one could consider just the space is ending, terminating at that point. Right? You don't have to consider it as a section or like somehow blocking an asymptotically space. So like another way of looking at it is that if you look at an asymptotically flat space, and if you have the same sort of an ansatz, and you do a series expansion around RB equals infinity, then order by order, you can see that the coefficients of psi is set to 0. This and the most general solution that one can get in that case is a Reisner-Nordstrom solution. Like we are excluding rotations at this point. So if there is time independent solutions, it will be just right. So this is one way of looking at the no-hair theorem. And now it turns out to be not the case if you look at some finite RB. So if you're expanding around a finite RB, then the entire set of solutions in the series expansion can be characterized by 6 free parameters. Actually, this way of looking at it, it is independent of the information that goes in at r equals 0 or r equals rh. This is in general true. So in asymptotically flat spaces, no sort of scalar profiles are supported. But if you're looking at some the boundary at some finite RB, then you can determine the entire series expansion as a function of the 6 coefficients, which you can read off by from the fully backreacted solution. So, but at this stage, I'm just trying to say what I think. So, but isn't that just because the boundary is some sort of a null boundary, whereby you don't have anything that comes? Like, yeah, the boundary, how the boundaries specifics are managed by like keeping the boundary at r equals rb is something that is, yeah, yes. Yeah, once you put the scalar and yeah, what you, no, so that's the point here, that there is no, once you have a scalar that is introduced in the box, there is no way in which you can take an RB going to infinity limit. The solutions are just exactly 0. Yes. Yeah. Yes, those are quantities defined at the bound. So again, that also brings another point here, which is that the quasi-local energy definition doesn't fit into the computation of the, like, if you're computing the free energy, you can compute it using the E minus Ts minus mu q, or you could compute it directly by evaluating the on-shell action. So this quasi-local way of defining things do not fit the case, because one of the way in which one could look at that is that if you're looking at an Einstein-Maxwell system, like, you could look at some R equals RB hypersurface as part of an asymptotic setting. So you could still have a reasonable quasi-local definition where you can take the hypersurface to go to infinity. But if you're looking at some the case where you are trying to put a scalar also, a non-trivial scalar, then there is no way of taking RB going to infinity limit. So the way in which quasi-local quantities are defined doesn't add up to computing the free energy using the on-shell classical action. Yeah, that's also one thing to be. So, but we would guess that, like, the chemical potential and charge, which are just dependent on the Maxwell field, the definitions of those hold. It's the quasi-local energy definition that somehow has to be modified or appropriately. But like, but we'll just plow on from here with the assumption that the free energy is just the on-shell classical action, and from there we can define the full set of phase diagrams. So we can classify the phase diagrams. So the full set of solutions here includes 2 different cases. One, so in all the cases we'll be looking at the boundary conditions for the scalar, which is Dirichlet, and for the Boson star, which doesn't have any horizon, we set all the derivatives of the functions at r equals 0 to be 0. So there are no kinks at r equals 0. And also, like, you do a series expansion about r equals 0 and consistently solve the equations of motion, you will get g of 0 equals 1. And the entire set of solutions will be parameterized by these 3 quantities. So h at 0 is somehow arbitrary, because at the end you have to rescale so that your boundary metric looks exactly the same as the flat space boundary metric. So one could take h to be arbitrarily set to 1. At the end we'll rescale it. And for a given psi of 0, we choose a phi of 0 such that the boundary condition at r equals rb is satisfied. For the hairy black hole, we'll have to set at RH these two boundary conditions. This is basically the definition of the horizon, and this is for the regularity of at the horizon. And here, the entire set of solutions will be again parameterized by three quantities, which is the psi at RH, the electric field at RH, and the H at RH, which is again an arbitrary quantity. So this solutions which are fully backreacted are solved by like shooting these numerical methods. So the boson star has like 0 or arbitrary temperature and has a smaller free energy than flat space, and is a second order phase transition from the lab. So if we look at psi of R profiles, which is very, very small, then one could look at the probe approximation where the fields G, H, and phi will solve to G and H will just give flat space coordinates, and phi will just be a constant. And then you can constant, which is chemical potential mu. So psi of R will be, you can exactly solve, it's a linear equation at that stage. This is just at the probe approximation, so you will know where the boson star instability actually happens. So we'll be looking only at the first mode. It will be like the first eigen mode, and we'll get the condition like. So the fully backreacted solutions are computed numerically. This is a plot of like the functions. So this is psi, this is phi, this is H and G. It is x-axis is R, and this is so psi goes to 0. Phi is an increasing function as well. G and H, and this is done such that at the end both of them like G times H at RB equals 1 gives you 1. So essentially GTT is 1. So these are plotted for a couple of different. It's just a existence of solutions plot. So now if we look at the hairy black hole, it's a finite temperature solution, and as the hairy black holes will in general have a lower free energy than the black holes with the same T and mu. The second order transition from a Reisner-Nordstrom black hole. And the instability in a similar way, where you take psi to be very small, ignoring all the psi square terms, you will get an Rn solution times and this equation, which you can solve for given values of Rh and small q. Shoot for the capital Q, and you'll know where for each Rh for a given q does the hairy black hole instability have. So here we look at some couple of solutions where the fully backreacted case. So psi, this is phi, and this is G. So if you look at G specifically, what happens is that as you increase the backreaction, the G starts curving inside. Like if you increase the profile of psi within the box. And it could be seen that at some point of psi of RH, this will actually start hitting 0. And it looks like there will be another horizon that forms. But luckily, these solutions never arise until the solutions that we have computed, because before this happens, this hairy black hole will be no longer the thermodynamically favorable phase. So those kind of errors, those kind of difficulties are avoided. So now let's look at the phase diagram. Phase diagrams are essentially completely categorized based on the values of Q, which is the Maxwell to scalar coupling. So the metric is rescaled at GTT. GTT at RB is 1. So the temperatures of hairy black hole and flat space at R equals RB are the same. Time circles basically are the same. So this makes the background subtraction using flat space very straightforward. And yeah, so if we look at scan throughout the Q, the values of Q, we'll end up seeing that there are 3 different types of phase types. The first type is where Q is less than infinity and is greater than some cutoff value Q1. So here you can see that all 4 phases are existing. This is the usual Hawking page-like curve, which is between the flat-spaced empty box and the Rn black hole in the box. And then the flat space transits to a boson star. Again, you compute this free energy, the first order curve between boson star and Rn black hole semi-numerically. And then the S2 is the second order transition from Rn black hole to a hairy black hole. This is the saturation curve that existed in the case of the Risen-Nordstrom black hole that we looked in the beginning. And there will be another first order transition between Boson star and the hairy black hole. And this dotted line, it's the region where we were not able to completely fix the solutions because it's the black hole RH size is almost becoming very close to the RB itself, and it's a bit difficult to keep the shooting program. But either way, one knows that when you are looking at RH that is very close to RB, the possible solutions that exist are very small, so it has to pinch off towards this point. So this is just it's not an exactly plotted curve, but we can see that there is a region in which the hairy black hole is the thermodynamically favorable. So this, these are for Q equals 40 and Q equals 100. You can see that this is the exact plots, which is why we don't have the result for what happens in this region. So around here, the entire region will be Boson star above this particular region. So also one can see that as Q decreases, this hairy black hole instability curve is curving upwards. And around Q equals 40, already the hairy black hole, the region in which hairy black hole can exist is very small. And the Q1 around 36, below Q1 is around 36, you'll see that this will transit to the next type of phase diagram, where the hairy black hole instability is not happening in a region where the Rn black hole in itself is a stable phase. So here we have only three possible phases. So the F1, which is the usual talking phase-like transition, in between the Boson star and the Rn black hole. And this curve goes and eventually hits the saturation curve. And there is no hairy black hole for Q less than 30. And now also we saw that for the Boson star instability, mu Q is equal to pi. So from there, if you keep reducing Q, we can see that the mu will keep increasing. And at some point, this particular second order transition will happen above the region in which the Rn, so before we just go to that, these are a couple of plots for Q equals 30 and 36. So we get here when the Q is very small and the Boson star instability happens at a point above this particular cutoff, which is around 1/3. So here also there are three different phases, but it's kind of a trivial phase diagram in some sense. So so the key takeaway points from this entire talk is that we have considered the Einstein-Maxwell system and extended the work of Braden et al. And did a full detailed study of the phase diagram in the grand canonical ensemble. We also solved the fully backreacted Einstein-Maxwell scalar system in a box and find hairy solutions. And these hairy solutions are the Boson star and hairy black hole, which are exactly the same as one would find in ADS. And then we find that they can be thermodynamically favorable phases.